So today we are going to study something in operational amplifiers when applied as filters. So filters are basically circuits that are there to limit or to allow certain range of frequency to pass. So there are basically three types of filters. Applied. These include low pass filter. Roman 2 is high pass filter. Roman 3 is the band pass filter. So I'm going to start with the low pass filter. So we shall have a sketch of this diagram first. Low pass filter. So when you look at this diagram, for us to have a low pass filter, we have the resistor connected in series with the input, which I refer to as the VI, while the capacitor is shunted with respect to the input. Therefore, the low frequencies are going to be passing through the resistor R and will be conducted to the amplifier, while the high frequencies are going to be grounded. And therefore, in this case, we shall be conducting more of low frequency than higher frequency. So we talk of the low pass filter. So it provides a constant output. It provides a constant. It provides a constant output from a DC input, from a DC up to an AC input, which is at cutoff, The meaning of cutoff is the frequency at which, when reached, the conductivity is not allowed. So when we're moving from low frequency to high frequency, the margin at which the frequency changes to high frequency, the frequency changes from low to high, is whatever I refer to as the cutoff. And at this margin, the conductivity of the low pass filter is reduced to zero. So we are going to have a sketch of the output waveform so that we are able to understand how this is able to be conducted. The output characteristics. is the gain. So when look at this output characteristic, we are starting at this point here, which I'm referring to this, and this is the cut-off frequency. So at this area we are still at low frequency, but just above the cut-off, the frequency changes to high value. The conductivity reduces to almost zero. This is a practical low-pass filter. When it's an ideal low-pass filter, we shall have the broken line being the margin, and we shall have it drawn like this. So this is ideal, the ideal situation. And this is the practical situation. So with the ideal, we shall have the cut off here. We shall have the cut off frequency. The cut off frequency, and we shall also have the gain here. So basically, this is what it is. So from the look at the diagram on a low-pass filter, the gain is normally retained from the functions of operational amplifier, and therefore the gain of the low-pass filter is given as gain is supposed to be 1 plus RF over R1. So the cut-off frequency is given by FCH is 1 over 2 pi RC, where R is the resistance, the resistor at the input, and C is the capacitor at the input. Let us take note of this. When a single resistor and capacitor are used to determine the cut-off frequency, then the circuit is also referred to as a single pole, referred to as a single pole low pass filter. If two resistors and capacitors are used at the input, are used at the input, to determine the cut-off frequency. The circuit will be referred to as a double pole low pass filter, or sometimes referred to as second order low pass filter. So we can have a sketch of second order low pass filter so that we compare it with the first order low pass filter. So I'm going to have a sketch of that. So when you look at this diagram, we are realizing that there's a capacitor between the two resistors and also the capacitor at the input. So these capacitors work with this one and this one will work with this one. So in this case, at the input end, there are two resistors, which is R1 and R2, and also there are two capacitors, C1 and C2. For this case now then, we're talking of the second order because of the positioning of the input capacitors, which are 2, and the input resistors, which are 2. The gain of this second order low pass filter remains the same as the gain of the first order low pass filter, simply because at the output end we still retain the same circuit. At the output end we still retain the same circuit. Therefore, the cut-off frequency of the second order low pass filter is given as FCH is supposed to be 1 over 2 pi the square root of R1, R2, C1, C2. Another thing we need to understand on this, another thing is that the gain of the second order low pass filter remains the same as the first order low pass filter and is given as So we're going to study another type of filter. Second filter is the high pass filter. We are going to have a sketch of this also, let me have first order high pass filter. And we have a sketch of this now. So this is how the high pass filter will look like. So in this case, the capacitor is connected in series with the input, and the resistor is shunted with respect to the input, but the output circuit remains the same. And this follows that the magnitude, this one will not block the frequencies of the low frequencies more than the higher order frequencies. The high frequencies will be able to go through the capacitor and to the operational amplifier, but the low frequencies will be blocked by the capacitor. So in this case, it's going to allow the frequencies of the higher order in its characteristic more than the frequency of the lower order for purpose of conductivity. So it allows frequencies of higher order magnitude. It allows frequency of higher order magnitude. Higher order magnitude, while blocking frequencies of low order, while blocking frequencies of low order magnitude. We shall have a sketch of its output waveform. So we talk of the output characteristics. We shall have this. This is still the frequency. So this is the cutoff, FCH. This is the gain. So this is practical situation, and this is ideal situation. So when you look at this, we are going to realize that for practical situation, the curve is not actually vertical. It's somehow in an increasing order, so that the switching starts when we are slightly above the cutoff frequency. So at this frequency, between this point and this point, the frequencies have been blocked by the capacitor since they are still low frequency. But as they transcend to high frequency, they are able to be conducted, and the conductivity improves up to this point. So this is what we talk of the practical. But when we look at this, we also have the gain and the frequency, which remains the same. So let us have, how about second order? Low pass filter. So this is an example of a second order low pass filter. A high pass filter, not low pass filter. It's a second order high pass filter. Not low pass filter, second order high pass filter. When you look at this, then we are able to see that at the input end, there are two capacitors, C1 and C2. C1 and C2, and also the R1 and R2. But in this case, the capacitor is in series with the input. Then it creates a high order, second order low pass, high pass filter for that purpose. But also, we're going to realize that when we have this as a second order low pass filter, the arrangement is only the reverse of the first order, and therefore the factors determining the second order low pass, second order high pass frequency are the same. So the cutoff frequency, is given by FCH 1 over 2 pi R1, R2, C1, C2. The gain which applies to both first order and second order is given by So we're going to study another type of application is the band pass filter. It's the band pass filter. So the band pass filter will allow frequencies of certain range to pass and block frequencies of certain range outside that the wanted range. And for this case, it's a combination of the low pass filter and high pass filter. So we are going to allow frequencies slightly above the low pass and all frequencies slightly below the high pass frequencies. And we're going to sketch for this purpose so that we are able to reflect on the type of the circuit that we need to know. So I'm going to sketch that. So this is a circuit that describes the band pass filter. And when you look at it critically, from the margin of the broken lines here, we can see these are identical circuits that we have done in the previous level or in the previous lesson. And when you look at it, this is a low pass filter and this is a high pass filter. And at this point of coupling, there's a direct coupling for them. So one of the things you'll get to know is that when you couple them directly, we're going to have the frequencies between a certain range of frequency passing only. And that is what we talk of the band pass filter. So it's a filter that is designed. It is a filter that is designed to allow certain range of frequency to be conducted. Certain range of frequency to be conducted. Whatever to be conducted, whatever referred to as the bandwidth, while blocking frequencies outside the range required. So we shall have a sketch of this so that we can be able to see how the two are found. So we're talking about gain versus frequency. Characteristic curve. So we sketch that. This end is frequency. This end is gain. And we're going to have so when you look at this diagram, then there's an evidence that when you combine the two circuits, then you shall get what is referred to as the bandpass filter. So the frequency between FC1 and FC2 is the frequency that will be conducted in the circuit. We talk of the bandpass filter. So we shall be able to combine the two and get a range of frequencies that will be conducted for the duration that is required. When you look at that also, at the lower end of it, there's a high-pass filter connection because we are only conducting frequencies above FC1. And at the right hand, we are going to have the low-pass filter. And because we are going to conduct frequency below the cutoff. So when the two are combined, then have the sketch of this diagram. So when you look at this, the low frequency will be conducted through the resistor R1 and to the first operational amplifier at the low pass end. And that the output of the operational amplifier will be coupled to C2. And it will be conducted, because it's on a high frequency, it will be conducted to the second operational amplifier and to the output end. And that's why we have this. So when this and this are reversed, then we come up with whatever another type of filter which we are going to discuss in the next step. Then we're talking about notch filter, or whatever sometimes referred to as a band stop filter. So a notch filter will only operate by blocking certain frequency between certain ranges. And for this case, we shall be able to have a sketch of a notch filter and have the characteristic curve. But when you reverse the positioning of the low pass filter and the high pass filter in the band pass, then we'll talk of the notch filter. So the characteristic curve, the characteristic curve looks like this. So we shall have here a low pass filter because we are passing frequencies between the lower end up to the FC1, and this is FC2. And this now becomes the low pass filter. And this is high pass filter. So from the characteristic curve, low frequencies will be conducted up to FC1 and thereafter, the blocking will take place until the frequency FC2 is reached, until the frequency FC2 is reached. Where the high pass filter will now conduct as required. We now conduct as required. We now conduct as required. Another thing we need to understand is the quality, the bandwidth for this kind of filter is given by the bandwidth for the band stop, for the band pass, for the band pass filter, for the band pass filter will be given by bandwidth is where Q where Q is the operating point, FO is the center frequency, and BW, which is given as FC1 minus FC2, is the bandwidth. So for when we look at whatever we have discussed today concerning the application of op-amp as a filter, we can get more notes that are more detailed, that will give you a detailed explanation with the examples in them on how this is applied. So kindly refer to the link below.